All right, so let's go ahead and we are back and let's go through our problem set 1 solutions. So first thing, let's look at this article and let's fill out our materials tetrahedron. So, I like this article. So this article is about, let's go through here. Basically, diblock copolymers. So you can basically stimulate these into self-assembly, and then they can perform pretty cool applications. So, for example, we can look at these. Depending on the sizes of the blocks, meaning the number of A polymer, B polymer, it basically changes the structure. And you can stimulate these block of polymers to do a lot of different kind of things here. And so we can see, like lipid particles, basically to form kind of like bilayers. And we can see some of these, and especially for basically stimuli responsive, basically nanotechnologies, especially for biomedical applications. So because we need these nanodiscs that are with a very specific structure at this nanoscale. So if we're filling out our materials tetrahedron, again, we have structure, we have properties, we have process, and we have performance. So the process would be we stick A polymer and B polymer together. We change essentially the volume fraction of that A and B, those A and B blocks, and then that changes the structure. So we have those nano stimuli responsive structures. That changes essentially the properties because each of those different structures will have various different properties. So, for example, it changes a lot of your basically surface tension, your surface energy. They're stimulated in different ways, their interaction potential, their chi parameter. So there's a number of different properties and their ability especially to interact with like biolipids. So the compatibility or the way that they can integrate depends on essentially that structure. And then that improves performance for all of these bio applications and stimuli responsive things. So beautiful. Excellent. Intermolecular ionic bonds exhibit localized electrons. No. Actually, let's see. Intermolecular? No, intra. So this needs to be intra. And then they are localized. They're either given away or they're either taken or they're given away, effectively. Intermolecular bonds, like hydrogen bonds, have an energy less than kT. Excuse me. Partial destructive interference is no signal on the intensity versus 2 theta curve. It needs to be perfect. Perfect destructive interference. Perfect. I can measure millimeter distances. To measure millimeters, I can use a laser. No, we need a lambda that's on the order of millimeters to measure those distances. Covalent bonded electrons are delocalized, and I can break. Nope, they are localized, and then they cannot break and reform at room temperature because they're around 200 kT in terms of energy. For Bragg interference, or Bragg diffraction, we need a series of perfectly arranged obstacles in a lattice. We also need lambda that's on the order of the distance that we're trying to do, and we need perfect constructive interference. So, a lot more than just that. Fantastic. What type of bonding will be exhibited by Cu? That will be metallic. Those bonds are delocalized, and they cannot spontaneously break and reform at room temperature. CaCl2. Let's look at what's our electronegativity. Cl is 3.16. Ca is 1. So 3.16 minus 1. So it is greater than 1.7. So that is going to be a purely ionic interaction. Those electrons are either... Actually, this is going to be, C is going to be plus 2, Cl is going to be minus 1. So their electrons are either taken or they're given away. And they cannot break and reform at room temperature. And then finally, PET. Let's go ahead and look. PET, chemical structure. Polyethylene terephthalate. And you see here, these big aromatic rings are going to have steric interactions. There's going to be carbon-carbon bonds here. There could be some, basically, dipole-dipole interactions, and because that O is going to be pulling electrons. So you're going to have a mix of covalent interactions and intermolecular interactions, specifically here, steric, and potentially some dipole-dipole interactions. And those intermolecular ones can break and reform at room temperature. Beautiful. CaCl2, Ca is our cation, 2 plus, Cl minus. CO2O3, CO will be 3 plus, O will be 2 minus. Fantastic. Cation, anion. Ooh, I like this. I'm trying to model the equilibrium distance of CO using my Lennard-Jones potential. It gives me my potential energy here. We're supposed to sketch where atoms repel and atoms attract. Basically here, we're going to attract. Here, we will repel. And you can explain your reasoning. If I were to go from state 1 to state 2, meaning they get further apart, then my energy increases. So I'm going to go from state 2 to state 1, meaning I'm going to attract it closer together. If I were to go from state 1 to state 2, meaning repel, separate, that's going to lower my energy. If I go from state 2 to state 1, meaning attract, it increases the energy. That's not going to happen. Cobalt has a metallic, where's our CO? Cobalt has a metallic radii of 1.25. So our cobalt, let's go ahead and open this up. So our CO radius is equal to 1.25. So we know that in our Lennard-Jones ULJ is equal to 4 times EPS times sig divided by r to the 12th minus sig divided by r to the 6th. Oops. So this is our Lennard-Jones potential. So we don't know what sig is. We don't know what epsilon is, but we know that our equilibrium distance will be 2 times this 1.25. So our equilibrium distance is when our Lennard-Jones potential's energy is minimized. So we're going to take the derivative, solve. When does this equal to 0? And when we do that, and we want to solve for r. So we know what this distance is. We know that sig can't be negative. It's a fitting function. So now we can just basically say here, solve. We know that basically this will be this distance 2 times COR. So this will give us our sig. So our sig is given here, and this will be in meters. Or actually, yeah, it must be in meters. We're also told that at that equilibrium distance, right, the energy of the potential at equilibrium is minus 5 joules. So we can say ULJ slash dot R goes to 2 times core is going to be equal to this. And we can pull this out and say, okay, but we know that this value must be equal to minus 5 joules. So our epsilon is equal to 5. Now we've got everything. There it is. Fantastic. So those are basically, that's how we would model it, and that's how we would draw and essentially utilize those values. That's it. See you next time in the next solution video. Bye.